Hello my esteemed viewers. In these tutorials, the concept of bending moment and shear force that would occur in a beam is clearly explained. This forms tutorial number 1 in the series that is set forth to glide through different aspects of bending moment and shear force in the beams in the order of increasing complexity. We see beams in the future course of higher semester or after our degree, that particularly civil engineers, mechanical engineers, aeronautical engineers, industrial and production engineers, industrial and management engineers will see the beam as very significant and important component in taking huge loads in a structure. We see steel beams, steel beams connected together forming a steel structure, and concrete beam fully encased in a mesh of reinforcement, and beams beneath a bridge that we can see, and beams in an industrial structure, the cantilever beams that we can see over here, and concealed cantilever beams that are available in a canopy, which are holding this huge canopy, and the beam sections piled together, and they're very important and very significant and widely used I section of a beam. And therefore beams will galore. Beams are there everywhere. Components in a machine too, or in automobile, we can observe beams. Here is a leaf spring beam which will take the impacts of the wheel when the wheel moves over humps and dips in a road, and this shaft will also occasionally act like a beam. And here there is a shaft axle of a vehicle which will also behave like a beam. And here this is the shaft of a floor mill, and this is shaft of a lathe. And here the windmill is an example of a cantilever beam, as if it is planted on the earth, and it will take the wind load and the loads at the end of this, that is windmill tower, will have the loads of these rotating fins, and it behaves like a cantilever beam. The most intriguing question is, what is a beam? How do we define a beam? Beam will look like this, with the longitudinal dimension too huge, too big, with the cross-sectional dimensions too small relative to longitudinal dimension. And beams are always supported, and beams are always laterally loaded. So taking the coup from the articulation of this bridge, we can define the bridge to be a component in a structural system whose longitudinal dimension is large in relation to cross-sectional dimensions, and which is laterally loaded. Beams are supported, and we need to go through different types of supports because we need to find out the support reactions, and depending upon the supports we will get support reactions. And first of all, we will have what is called as roller support, to be called as a very simple support, and the typical real world example is the rollers provided beneath a bridge. And at they're providing the roller support at one end of a beam is a must, because rollers, if the beam is subjected to an inclined load, the vertical component of the inclined load will generate a vertical reaction over here at the pin, and the horizontal component of this inclined load will make the beam to move relatively. It will provide a flexibility for the translatory motion. This could be a braking force in a beam, in a bridge, or it could be thermal stresses, longitudinal expansion of a beam. And when due to moment of this vertical force and the momentum, the beam would rotate. Therefore, a roller support has only one reaction, a reactive force perpendicular to the plane of rollers. It has 2 degrees of freedom because it can move horizontally for a horizontal load. It can rotate with respect to the hinge for a moment which is external. And of course, the roller support is a must, as I told earlier, because it will allow longitudinal movements due to temperature effects, particularly in a bridge. Hinged support is the next one, and hinged support is used at the other end of the beam. If in a beam the two extremities in two extremities. One of the extremities must be roller support, the other extremities must be hinged support. Hinged support will look like this. The entire structure can rotate with respect to this hinge. And here it is, the simplified version of a hinged support is over here, and if you apply an inclined force over the beam, the vertical component will generate a vertical reaction, the horizontal component will generate a horizontal reaction because it doesn't move horizontally, and for a moment this will rotate. Therefore, hinged support will come with only 1 degree of freedom. Hinged support will come with only 1 degree of freedom, and whenever a hinged support is given, we need to find out the vertical reaction and the horizontal reaction. Of course, horizontal reaction would crop up if and only if there are horizontal forces in a beam. Fixed support is yet another support which will come like this, and the beam is firmly fixed over here and it cannot move horizontally or vertically. And here are real world examples of a fixed support. This beam is fixed with the help of rivets or the bolts. This column is fixed to the ground or to the steel plate with the bolts, and here a steel column is really embedded in concrete, thus achieving a kind of fixity. And if we apply a vertical load, it will create a vertical reaction over here, and if we apply a horizontal load, horizontal reaction is generated, and for this moment, this force into perpendicular distance, and this is the moment, and this moment will immediately generate a moment reaction, fixed moment over here. Therefore, in a fixed beam, there will be 3 unknowns and there is no degree of freedom. It can neither move horizontally, it can neither move vertically, nor it can rotate. Therefore, fixed support has all the reactions present: a vertical reaction, horizontal reaction, and fixed moment. It has 0 degrees of freedom. Therefore, probably this is the reason why a civil engineer always prefers fixed beam or fixed support or fixity at both the ends of the structure. And we will go through types of beam. There are types of beams that we come across in the real world. This is a simply supported beam. A simply supported beam will have a single span, and at the 2 extremities, one of the extremities will be roller support, other extremity will be hinged support. It is a single overhang. Possibly this is a inside accommodation, maybe a room, and outside there must be a canopy or some kind of a chajja. And this slab goes beyond the support at only one place, therefore it is single overhanging beam. But here there are double overhangs, one this side, one this side, and this is the cantilever beam. It will have a typical cantilever action, that it has only one fixed end and the other end is free. And this is the continuous beam. Continuous beams will really appear in case of continuous bridges and industrial buildings. Of course, continuous beams are also there, and analysis of continuous beams or drawing shear force and analyzing shear force and bending moment in continuous beams is beyond the scope of this particular tutorial. And fixed beam is there. Fixed beam will come with 3 reactions over here, 3 reactions over here. And we have only 3 equations of statics, fundamental equations of statics. Therefore, this becomes indeterminate structure. And here again there are 4 support reactions. Therefore, this will also become an indeterminate structure. Of course, indeterminate structure analysis is beyond the purview of this tutorial. Okay, beams are loaded with typical loads too, and here there is a concentrated load, and you cannot find in reality, in the real world, a concentrated going like an arrow. Of course, they are seen in their semblance, and here is a footing and here is a column, and column load over this footing can be considered more or less as a concentrated load, because the area of cross section of this column is comparably low when compared to area of cross section of the footing, the supporting surface. The wheel loads on a bridge top or a bridge slab are typical example of concentrated loads. And here is the rail load. Typically rails will have some kind of a point contact, and they will apply literally in a physical sense, of course, concentrated loads. They are the best examples of concentrated loads. Of course, they will be moving. uniformly distributed load. This is the widely used load, usually widely hypothesized load. And here it will be represented like this. This is a beam of span 3 meters, and the intensity of uniformly distributed load is spelled out like this: 20 kilonewton meter. That is, per 1 meter of the length of the load, it would have transferred around 20 kilonewton. Of course, there is no way to directly deal with this UDL when we take up the analysis of the beam. Therefore, UDLs will be generally considered as a special kind of a rectangle where height is the intensity of load and the length is the span. And the area of this load rectangle will be taken as equivalent concentrated load. And the centroid of this rectangle happens to be the joining of the diagonals, and it comes exactly at the center. Therefore, whenever we encounter UDL, which is the reality, of course, they can be called as equivalent loads because effect of a concentrated load is completely different from effect of a UDL. And this UDL has to be replaced by a equivalent concentrated load, which is nothing other than the area of the load rectangle, and it comes 20 kilonewton per meter into 3 meter, the length of the rectangle and the height of the rectangle, and meter will get cancelled, and we will get a 60 kilonewton load acting exactly at the center. So it's very important to remember whenever UDLs which are prevalent in the real world is applied over the beam. For the analysis, whenever we consider the analysis, we need to convert them into equivalent concentrated load. Some of the examples are self height of the beam itself is a UDL. Water load on the bottom of slab of the water tank is also an example of UDL. Wherever things are uniformly loaded, there exactly UDL comes into picture. Of course, there is another category of load which we will occasionally see. This is uniformly varying load. This is a special kind of a load wherein the intensity of loading is too high over here, very high over here, and it gradually becomes zero. And such a situation can be obtained when we construct some kind of a triangular wall on a beam, or typically the water pressure distribution over a wall, let's say a water tank, is typically triangular in nature with zero intensity of pressure over here and reaching maximum intensity of pressure over here, and the value of this particular arrow will be equal to height multiplied by density of water, that is 10 kilonewton per meter cube. And this is a typical example of, so that means whenever the walls of a water tank is to be designed, it should be considered as a uniformly varying load or triangularly varying load. Once again, there is no direct method to deal with them directly. Therefore, it should be considered as a load rectangle, as we considered for UDL as a load rectangle, where height is the intensity of the load and base is the span of the beam. Okay, and we will multiply the area of this triangle, half into base into height. Height is 6 kilonewton per meter. Meter will get cancelled, and we will get 80 kilonewton. And 80 kilonewton is to be placed at the centroid of this particular triangle, which happens to be h by 3 from this base or this end, and 2h by 3 from this apex. So h by 3 happens to be 6 by 3. Therefore, at 2 meters we will find a equivalent concentrated load. Of course, here again the action of the force, the typical action of the force in triangularly varies is completely different from its own concentrated load. Of course, with the meticulous methods not available, we will regard this to be the equivalent load, and this will be considered only while the analysis, as I said earlier. It is also possible to apply what is called as concentrated moment over a beam. A concentrated moment can be cooked over a beam. Let us say this is the beam, a bracket is welded over the beam, and for some reason we are going to apply the load like this, and definitely the load into height will generate a moment, and we should be treated like a concentrated moment acting clockwise over the beam. Again, concentrated moments will have bending effect and also rotational effect. Okay, as an external force, it has a rotational effect. As an internal force applied over the beam, it has the bending effect. Now, concentrate. Before we discuss on bending moment, we need to understand what the moment is. And of course, we have heard a lot about the moment in engineering mechanics. Here is a hammer, and we need to pull this nail just out of this wooden block. Therefore, what we do is we will apply the force over here. We will generate a moment. This moment will get translated into tension in this particular nail, and nail will be unnailed. And here is a typical example of moment in action. This is the fulcrum, this is the seesaw. The moment generated by this child is more than the moment generated by this child. Therefore, clockwise moment supersedes anti-clockwise moment. Therefore, this fulcrum is not balanced. So the weight of this girl or this child and the perpendicular distance will generate a moment which is external to this fulcrum. This seesaw will never bend. And if there is a fixity over here, it may bend. Right. And here is another example wherein the anti-clockwise moment generated due to this weight over this particular support is more when compared to clockwise moment over here, justifiably so. Therefore, it is getting lifted. It is not in a balanced state. Moments are not balanced over here. And here, when it comes to, people say, when it comes to nature does it better whenever balancing act is concerned. Look here, it's a balanced stone, one above the other. And here, external moments are balanced. And here again, there is a fulcrum, the central point. Okay, the moments are not balanced, external moments. Therefore, the system is not in equilibrium. Here, there is a balance, and at the balance, fulcrum is at the center. Therefore, load over here, which will create an anti-clockwise moment with respect to the center, is equal to effort, the weight, which will create clockwise moment. Now, we will talk about bending moment, the heart of the matter of this particular tutorial. There is a beam, a cantilever beam. It is fixed through adding the weights over here or by some means, and we will apply the load over here. Immediately it will create a reaction, vertical reaction. It will also create a moment of fixity. If this is clockwise, 2 into some force, and it is going to create anti-clockwise support. Anyway, it will bend. It will sustain as long as it can, but it will bend. So this is really bending action. So the bending moment, which is load into this perpendicular distance, will really make the beam to bend. And it acts exactly over here. And we can calculate the value of bending moment at different sections. And as we go from here it is 0 because there is no moment arm. As we move inch by inch over this beam, we will culminate in the total bending moment, which will be very critical at the support. Therefore, bending moments will bend the beam. Bending moments are purely internal resistance offered by the beam against bending. Of course, this internal resistance we are going to refer in a later course of study as moment of resistance. For time being, it's better we understand the bending moment is internal. Bending moments are created by external lateral loads added over the beam. And in a typical cantilever beam, we will see top tension, bottom compression, convexity upwards, concavity downwards. A fiber over here at the top will be elongated, and a fiber over here will be compressed. We can check this by putting some glue in our palm and allowing it to dry. And if we bend this palm, and we will feel some kind of an excruciating pain at the top of the palm, while the fatal lines will close at the bottom. And if we happen to make small cracks over here, and these cracks will wide open at the top and it will close at the bottom. So tension at the top, compression at the bottom. This typical kind of a bending is called as hogging bending moment. And in our course of study, we always treat this hogging moment to be negative. And here is a simply supported beam. There is a load applied. Immediately it will generate reactions, and these reactions will making the beam to push up, that is bend up, and this will push it down. Therefore, the beam will obtain some kind of a saucer shape. It's some kind of a saucer shape, wherein we will see top compression and bottom tension. And this is typical beam behavior as far as simply supported beam is concerned. Therefore, simply supported beams are subjected to sagging moments. They sag like a string. They sag like a let us say the saucer. They take the shape of a saucer. Tension, compression top, bottom tension. And here is a single overhang beam, and single overhanging beam, if loaded like this, will bend like this. These are typical approximate bending behaviors, and these figures are of great interest when we further our course in this bending moment and shear force analogies. And here is a W overhanging beam. This is the kind of bending: top tension, bottom compression. Here bottom tension, top compression. Once again, there is a reversal of bending moments and reversal of bending action, reversal of bending behavior. And we will take a typical example as to how we can calculate the quantum of bending moment. We need to define that. When it comes to analysis, we need to define how we can compute the bending moment values and shear force values. Here there is a UDL, and as we have understood, UDL cannot be directly dealt with. We convert that into a concentrated equivalent load, that is 10 into 2, that is 20 kilonewton acting exactly at the center. Therefore, the moment Rm is 1 meter. This will be able to generate 20 into 1, 20 kilonewton meter of bending moment, and this is the reaction, of course. Therefore, this reaction and the bending moment from the top will make the beam to hug. It will have convexity upwards, and of course there is a reaction over here, and this moment and this reaction are purely in external reactions, external reactive forces, which are there to safeguard the equilibrium of this the cantilever beam. So as far as the internal of a beam is concerned, it is not really happy because it is subjected to bending. So therefore, bending moment at A equal to the load, okay, 10 into 2, the equivalent concentrated load into moment Rm. So 40 kilonewton per meter. And in the same token, if we consider the simply supported beam with UDL, and we will translate this UDL into a concentrated load 10 into 2, the intensity into span 20 kilonewton, and we will find the reactions. Since the loading is symmetrical, acting exactly at the center, it will derive 10 kilonewton here and 10 kilonewton over here, and we will find the bending moment over here exactly at the center. Okay, because center is the crucial section, and if you find that it is 10 into 1, 10 into 1, the moment, the bending moment, minus, okay, while this reaction will make the beam to go up, sag, the portion of the UDL for half the length of the beam will make it to hog, because it will bend it downwards. So it is 10 into 2, okay, this is 10 into 1 into 1 by 2. Okay, so this is a minus effect, this is a positive effect, because we always consider sagging to be positive and hugging to be positive. Therefore, at this section, exactly 5 kilonewton per meter of bending moment will be in action. That is the root cause for the beam to take maximum bending at the center. It's something like this. If we can foresee this particular section, in case of a T section, this is how it bends. Of course, it is an exaggerated sketch, exaggerated sketch, but we can clearly see the effect of the bending moment. The moment can rotate the beam, while bending moment can bend the beam. Beam sags. So concept of shear force. Consider a load, take a load over here, and consider the portion of the beam. Let it be 40 kilonewton. 20 kilonewton would be the reaction, and we will consider a section just to the right of this force, and here we will find shear force, the reaction over smarts, because by considering the section to the right of this particular load, we are eluding the effect of 40 kilonewton, and we are considering only the effect of the reaction. And of course, if it is simulated vaguely, section just to the right of the load will receive shear force of 20 kilonewton, because this predominates, this reaction predominates, because the effect is the beam shearing up with a possible crack over here. And if we consider a section over here, we want to include the effect of the applied load. Here to elude the effect of the load, here to include the effect of the load. Section just to the left of this load is SF equal to 20 positive up and 40 minus. Therefore, we will get a negative shear force. And if we simulate vaguely, here the load pervades. Together with the reaction, this portion of the beam will go down, or this portion of the beam will rise up. There can be a relative movement owing to the shear force. So shear force has a sliding effect. Shear force has a shearing effect. Shearing effect means there can be relative movement at a particular section over the planes of cross section. And we will take a typical example, simple example, and we will thoroughly analyze the bending moment and shear force. And first of all, we need to calculate the reactions, because it is a supported system. And here 20 kilonewton, 20 kilonewton, and 20 kilonewton, the loading is symmetrical. How do we determine whether the loading is symmetrical or not? Look at the center of the beam. Look rightwards and leftwards. And the force available over here should be same in magnitude in both the cases, and equally spread and equidistant from the center. That means if we were to fold this beam, and we will get the mirror image of AD in dB. So it's very important, because by identifying whether the loading is beam and loading is symmetrical, we can avoid the drudgery of calculation of support reactions. See, here I can directly place RA equal to RB equal to all the three loads added divided by 2, 30 kilonewton. So the beam will experience a reaction of 30 kilonewton here and here. Now, in order to find out the shear force, we will just move from this end to that end, from this extremity B to A, without leaving an inch of a beam. Or sometimes we will stop. Whenever we encounter a load, concentrated load, we will stop, and we will see what is the effect to the right of that particular load. By considering right of a particular load, when we move in this direction, we want to elude this particular effect, and we want to consider the force effects to the right of the section. So we will take a typical example. We will move very slowly with some simple simulation, and here is a reaction 30 kilonewton, and here is the section just to the left of B, just to the left of the support, because we cannot take sections over the support. We are not bothered about the supports, we are bothered about the beam. Therefore we will move just. Whenever it comes to plotting, it is just to the left is the point itself. Okay. And SF just to the left of B equal to 30 kilonewton. And positive effect prevails because it is force upwards. And if we move the same, there are no loads intervening, therefore same effect will continue just to the right of E. SF just to the right of E is 30 kilonewton. And if you plot this, it will be like this. Here it is 30 kilonewton positive, same thing. Uniform shear will continue just to the right of E. And when we consider a section just to the left of E, something like this force will also be included. This is negative as it is going down, this is positive. So 30 minus 20. That should be 10 kilonewton. And if we happen to plot this, it is like this up till here, and here it takes a downward trend because shear force gets reduced drastically by 20 kilonewton. And if you were to plot, this is 10 kilonewton. Actually, this is the plotting, and here it drops from the earlier 30 kilonewton to 10 kilonewton. And this is the plot exactly we have done. So, okay, right. Now, SF just to the right of D. We will further move. We have crossed D, and you should notice that there are no other loads present. Therefore, the shear force remains to be same till the right of D. Therefore, SF just to the right of D is 30 minus 20, 10 kilonewton, and SF just to the left of D is 30. So it has crossed. Now it's over here. Both the forces are to be considered. This is 30, and this is 20, and this is 20, and we have gone to negative shear force. That is, beam is tending to move up due to the prevalent forces or reaction becoming outsmarting all the other forces. Anyway, at the joint the shear force will be same, but we will just get to know all those things. Okay, until then we will concentrate as to how we can calculate shear forces. So here 30 kilonewton moved constantly. There is a drop up to 10 kilonewton. 10 kilonewton continues just to the right of D. When we come just to the left of D, it becomes negative. It makes a negative to an extent of minus 10 kilonewton. So it drops. It goes. So this is the positive shear force diagram, and we have started with negative shear force. Now we are here, and we will move just to the right of C. We have no forces till then. Therefore, whatever that is just to the left of D will prevail just to the left of C. So that is just to the right of C, it is 30 minus 20 minus 20 minus 10 kilonewton. Same thing will continue. And when we move just to the left, like this over here, and even this force will also get added, and it becomes just to the left of C. It becomes 30, this one, 20, this one, 20, 20. And you should see, whenever we take a section, we have just algebraically added all the forces, including reaction. The reaction was positive, all other forces were negative. Anyway, algebraic addition is caring for sign, caring for positive effect and negative effect. It's not arithmetic sum. Okay, therefore a plot would look like this. A very important thing to be noticed is at the end we will get the ordinate. This value should be equal to the reaction value. So that is equal to, of course, with a negative sign, and the reaction here is 30 kilonewton. Therefore we have got minus 30 kilonewton. And it's very important to observe whenever a simply supported beam or any beam, as a matter of fact, is loaded with only concentrated loads, the shear force distribution diagram will look like steps. It's a stepped function with rises and falls. The rise or fall height is equal to the respective concentrated load magnitude over the beam. That is, this one is 20, this one is 20, this one is 20, and this one is 30, and this one is 30. So this is 30, and this is 20, and this is 20, that is also 20, and this is 30. Therefore, it is very important to remember that the distribution of shear force in case of a simply supported beam or any beam subjected to concentrated load only. Of course, there is no mix of issues. It's only concentrated loads. It is a stepped function with rise and falls of the step equal to the intensity of load just above. While finding the shear force, you must have noticed that at a section we just added or subtracted each new force to the right of a section. So justifiably or appropriately, shear force at a section of a beam may be defined as the algebraic sum of all the vertical forces either to the left or to the right of a section. So that means I have taken one more example. We are considering a section over here. 120 is the reaction, let us say, and we are moving inch by inch over the beam. It's over here at a particular instance. It is moved, and we are here just to the left of this particular point. Therefore, shear force here naturally 120 minus 30 minus 20 minus 40. Okay, so that happens to be a positive value. Therefore, shear force at this particular section is a positive shear tending to shear the beam, this portion of the beam up. Of course, there is a relative movement. If this portion is moving up, or tendency to move up, or tendency to shear up, the portion of the beam over here will be definitely moving down. It's always a relative movement. Shear force. Yeah, we will just take a look at bending moment and how we can calculate with the same problem. Of course, this is a very important point. While computing bending moment values, just to the right and left of load doesn't make sense. It doesn't hold water. As bending moment requires bending momentum, however small it may be. Just to the right means how just is this just? Therefore, whenever we compute bending moment, we will calculate bending moment at a section. So here we will just go once again inch by inch over the beam, covering all the points, all the predominant points. So whenever it comes to bending moment, the predominant points are supports 1, 2, A and B, C, the point of application of the load, D and E. So bending moment at B equal to 0, because if you apply a load, it will rotate because there will be a pin over here. Okay, due to simple support. Okay, it will rotate. Beam will never be susceptible to bending moment. It doesn't bend over the support. That's all. BM at E here. We will take the small section over here. We will take the section. We will dissect this portion of the beam and we will see here is the beam. Here is the section. Here is the reaction. And there is only reaction effect. The reaction will push the beam up, creating a kind of sagging. So it is 30 into 1. 30 is the magnitude of the load, 30 into 1, moment Rm. So 30 kilonewton meter. And if you come over here, bending moment D, okay, due to this reaction, the beam will sag up, and due to this load, the beam will hog down. So sagging moment by reaction, hogging moment by 20 kilonewton load. So if you just culminate the effect, it is 30 into 2 positive, sagging bending moment, 30 into 2 moment Rm, minus 20 into 1, 40 kilonewton meter. And at C, there is no need to come from the other end. Okay, we can move. This is the luxury, this is the flexibility while we compute bending moment. Okay, at the last point over the beam, not at the support, we can take an entry from the left support, that is from A. So here once again reaction prevails. This reaction will sag the beam up. Therefore bending moment there again 30 into 1, 30 kilonewton per meter. So important thing that we observed is at every point over a simply supported beam which is laterally loaded by downward forces, of course, without any moment or concentrated moment, the simply supported beam has to sag. Sagging moment is the signature of simply supported beam. If we generalize the expression for bending moment by concentrated loads, if we call bending moment equal to load into moment Rm over the beam, we will say Y equal to P into the moment Rm, P into X. It looks like Y equal to Mx, therefore the variation is linear. So bending moment at a section of a beam is algebraic sum of moments either to the left or to the right of the section. Right, we will plot this. We have calculated already. This is the positive bending moment value, negative bending moment value. The beam axis is taken as a reference. This is a graphical representation. This should not be confused with the bending nature of the beam. It is not the bending of the beam which is picturized, rather it is the magnitude of the bending moments which has been graphed. So therefore typically bending moment diagram is a graph showing the variation of bending moment at various sections. Here it is 0, and here it is 30 kilonewton meter, and here it is 40 kilonewton meter, and here it was 30 kilonewton meter. And since the variation is linear, as we have proved, it looks like a straight line equation. We have to just connect them by by straight lines. So this happens to be bending moment. Sagging bending moment is positive. The entire beam is subjected to sagging bending moment. So it's very important to realize the differences between moment and bending moment. Considered as an external force, bending moment is considered as purely internal to a beam which bends the beam. Algebraic sum of bending moments at a section need not be 0. It is 0 only at free ends and simple supports, while algebraic sum of moments with respect to a section must be 0 if they are simple moments for the sake of equilibrium. Moment can generate bending moment in a beam, and converse is really not achievable. From bending moment you cannot generate a moment. Instead we can generate what is called as moment of resistance, which is going to come in our next unit, of course, next tutorials. Bending moment can generate moment of resistance at a section of the beam. Moment has a rotational effect on the beam over the span, while bending moment has a rotational effect on the cross-sectional area of the beam. Simply cross-sectional area. Here is a bending moment at a section of the beam. Here is the bent beam. It has bent like this. This is the area of cross-section which has really rotated with respect to an axis called as neutral axis. And here the top is under tension, compression, therefore we have represented arrows towards the beam, and here it is subjected to tension, arrows away from the beam section. Therefore it forms a typical triangular triangular distribution, and here too. And we will later in the next unit or in the next tutorial series we are going to prove that there exists an axis which passes through the centroid of this particular section, coming to be called as neutral axis, which doesn't experience any stress. Stress here is 0, therefore it is typically called as neutral axis. Therefore bending moment at a section will create some kind of an unusual stress, okay, varying stress, okay, highest magnitude at the top, becoming 0 at neutral axis, increasing in the higher order up to the bottom layer of the beam. Therefore beams are called traditionally as the weakest components ever found by the civil engineers, because the same material is subjected to tension and compression in different zones. My esteemed viewers, with this we are making a close to this particular tutorial. In this tutorial we have understood as in threadbare as to what is bending moment, as to what is shear force, and the kind of supports, the kind of beams, kind of loads, etc., etc. In our tutorial we will dwell little deep into this particular topic with problems and possible relationships among bending moment and shear force. So if you have liked this video, kindly subscribe to my channel, and before I come back with the next tutorial in this series, bye and thank you.